Imagine setting an autonomous AI agent to work on a massive, complex codebase. For the first 30 or 40 steps, it operates flawlessly, executing instructions and moving data with frictionless precision. Then, at turn 38 out of 40, it makes a baffling mistake. It inexplicably ignores a critical rule it explicitly established back at turn 12. You check the developer logs. Turn 12's rule is recorded. The bad turn 38 is recorded. But logs are static. They give you the inputs and outputs, but they cannot tell you what the agent was actually holding in its working memory when it made the error. This diagram shows the timeline of those turns. Above turn 38 sits the model's context window. The issue is that this window is a black box. You have no way of seeing if the rule from turn 12 was pushed out because the model hit its token limit, or if it was still in there but buried under 25 turns of conversational noise. Without a mechanism to forensically examine that past working memory, finding the true root cause of the failure becomes an impossible guessing game. ContextTimeMachine was designed strictly for post-hoc investigation to solve this problem. It allows you to scrub through the history of a session and see exactly what the model saw at any given moment. Interestingly, this tool was built entirely by Neo, an autonomous AI engineering agent that handled the complex architecture and codebase end-to-end. The core logic making the tool possible is that a model's context window is deterministic. If you have the conversation history, you can mathematically reconstruct the exact data state of the model for every single turn. This chart demonstrates the timeline Navigator mode. As we move down the turns of a session, you can watch the tokens physically pile up in the mainframe, representing the model's memory filling with instructions, tool calls, and user inputs. Eventually, the token count hits the model's absolute limit. To accurately reconstruct what happens next, the tool simulates the model's specific eviction strategy. Here, older data at the bottom gets chopped off, how models like GPT and Claude handle overflow. But if you're using Gemma, the visualization recalculates, removing blocks from the middle while keeping the oldest and newest data intact. Mapping the exact boundaries of these limits turns invisible memory management into an observable mechanical function. Let's apply this back to our earlier error. We need to know exactly when the agent dropped the critical rule established at turn 12. The fact tracker tackles this by taking a specific text snippet and using local sentence transformers to embed it. It then scans the reconstructed context of every single turn, measuring cosine similarity to find matching content. This presence chart displays the life cycle of that rule. The solid green line indicates the rule is active in the context window. At turn 29, the color drops to red. That is the exact moment the fact left the model's memory. Isolating the exact turn where an agent stopped knowing a piece of information gives you the precise location to adjust your prompt or context strategy. But what happens when you have two agent sessions that started identically but finished with entirely different outcomes? One succeeds and the other crashes. ContextTimeMachine handles this with the divergence finder. It analyzes both the successful and failed sessions simultaneously to find exactly where their realities split. This graph illustrates the mathematical process. The tool aligns the turns of both sessions and constantly calculates the similarity of their context windows. They stay matched until the similarity suddenly drops below the 85% threshold. At that point, the system generates a side-by-side comparison of the two context windows, with the exact moment the differing content entered highlighted. By automating this comparative analysis, you calculate the root cause mathematically, rather than scrolling blindly through text files. Large language models are moving past simple chat interfaces. We are now trusting agents to execute long, highly autonomous enterprise tasks. Because of this operational shift, debugging methods have to evolve. Reading flat JSON files or catching errors while live monitoring a stream does not scale to an agent making thousands of sequential decisions. The mechanics of context management have become the primary technical bottleneck for building reliable autonomous software. Tools like ContextTimeMachine take the notoriously opaque nature of LLMs and apply rigorous, deterministic software engineering principles to them. True AI autonomy requires developer control. And that control is only possible when you have the power to forensically dissect and comprehensively understand